Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll demonstrate linear regression with Sklearn API. The objective of this collab is to demonstrate how to build a linear regression model with Sklearn. We'll be using California housing dataset for this exercise. We'll be implementing linear regression API that uses normal equation for training the model. Then we'll also train the model with cross-validation. After the model is trained, we'll evaluate the model with score function that uses R2 score. We'll also use cross-val score with different scoring parameters in order to evaluate the trained model with different scoring metrics. We'll also study the model diagnosis with learning curve and how to examine the learned model or weight vector. Let's start by importing some useful packages. Here we are importing some basic Python packages for manipulation and visualization. Then we import fetch California housing from sklearn.dataset module that helps us to fetch the dataset. The linear regression API that we are importing from sklearn.linear_model helps us to build the linear regression model. Then we have bunch of APIs imported from model selection module, and that helps us to perform cross-validation, plot the learning curve, and performing the shuffle split in cross-validation. We are going to use mean squared error as an additional matrix to R2, and mean squared error is implemented in sklearn.metrics module. We will be using pipelining for combining the preprocessing and the model in a pipeline manner. It's always a good idea to set a random seed so that we get reproducible results across different runs. So we are going to set the seed to 306. You can set it to any number of your choice. And we are going to use the plotting style that is Seaborn. First we'll use shuffle split cross-validation with 10 folds, and we'll set aside 20% examples as test examples. So you can see that here we are instantiating a shuffle split object with n splits equal to 10, test size equal to 0.2, and we have set a random seed. This particular statement creates 10 folds through shuffle split by keeping aside 20% examples as test in each fold. We'll be using shuffle split strategy throughout this notebook. The first step is to load the data. We have already discussed how to load California housing dataset in the last collab demonstration. So here we use fetch California housing API, and we set as frame is equal to true and return _x_y parameter to true. So because of this parameter, we only get features and labels. And since we are setting as frame equal to true, we get both these return values as data frame. So we have a feature data frame and we have a label data frame. So let's examine the shapes of feature matrix and the label vector. We can see that we have 20,640 examples, each with 8 features, and in label vector we have 20,640 entries. As a sanity check, we need to make sure that number of rows in feature matrix and labels match. And we can do that with assert statement by looking at the zeroth element of shape in feature matrix and label vector. The second step is to perform data exploration, which has been covered in detail in the last Colab demonstration where we studied California housing dataset. Then as part of step 3, where we are going to do preprocessing and model building, we start by splitting the training data into training and test sets. We do not access test data till the end. All data exploration and tuning is performed on training set and by setting aside a small portion of training set as a dev or validation set. So we perform train test split by using a train test split class from sclearn.model_selection module. The train test split splits the given feature matrix and label vector into training and test feature matrices and train and test label vectors. Again, in the similar manner as feature matrix and label vector, we also examine the shapes of training and test sets. Here, we have got 15,480 examples in training and 5,160 examples in test. We also perform a sanity check to make sure that the training feature matrix has the same number of rows as training label vector. And also we perform the same check in the test set too. So we use again assert statements to make sure that these conditions are met. Next, we build a linear model with default parameter settings of linear regression API. We'll make use of pipeline API for combining data preprocessing and model building. We'll use standard scalar for scaling all the features to the same scale, followed by linear regression model. So this pipeline that we have built here has two parts. The first part is feature scaling, where we use standard scalar object or standard scalar class. Here we instantiate the object of standard scalar class that helps us to bring all features on the same scale. Then in the second step of pipeline, we have linear regression object instantiated that helps us to perform linear regression with normal equation. Once this pipeline is constructed, we can train the pipeline by calling the fit function on the pipeline object. And we supply the training feature matrix and training label vector as parameters to the fit function. Now that we have trained the model, let us check the estimated weight vectors. And these weight vectors can be accessed through intercept underscore and coif underscore member variable of the linear regression object. So here, note that in pipeline we have two stages. First is feature scaling and second is linear regression. So we can access the linear regression object by using the index in linear regression pipeline object of the pipeline class. So we can access this particular estimator by lin underscore reg underscore pipeline of -1. And you're very well aware of how indexing works in Python. So since we are trying to access -1 index, which is last step in this particular pipeline, which is linear regression. So this particular expression gives us the linear regression object, and then on that object we call intercept underscore, which is the member variable of this object that gives us the weight for the intercept, that is W0. And when we access the coif underscore member variable of the same object, we get weights for the remaining parameters. So intercept W0 is 2.07 and the weight vector that contains m entries W1, W2 all the way up to Wm, where m is the number of features. And since there are 8 features, you will see 8 entries over here in the weight vector. Now that model is trained, let's move on to the next step, which is model evaluation. In evaluation, we will first use the score method to obtain train and test error between objectives. We'll use, we'll use the score obtained for estimation of model performance, and that estimation is based on what we get in the test error. We also compare training and test error for model diagnostic purpose, where we want to figure out whether model is underfitting, overfitting, or model has gotten the just right fit. So what we do is we call the score method on the pipeline object. So what pipeline does it? It takes this feature matrix, first applies feature scaling, and then call the predict, and then it scores based on the predicted value and the actual value of the labels. So we get this score, and by default this score is R square, or coefficient of determination. We perform the same thing with the training set. The score method returns R2 score, and since this is a score, higher the better. And we can see that we have slightly higher performance on the training set than the test set. And remember that the best value in R2 score is 1. So we are far from being the best, but we have a decent performance here. Another thing to note that the performance is comparable on test and training, but it is not that high, and this could well point to the underfitting issue in the model. Now in score method, we have calculated the score on one fold that was selected as a test set. So that's why it may not be all that robust. In order to obtain robust estimate of the performance, we use cross-validated score with cross_val_score API from sklearn.model_selection module. This helps us to calculate score on different test folds through cross-validation. So the way we call cross_val_score is by specifying the estimator, the training features and labels. We can also specify what kind of scoring function that we want to use. Here we are specifying negative mean squared error. So this is negative of the mean squared error, and this is a scoring. So in scoring, the score higher the better, and error, if we are calculating error, the lower error is the better error. And we have seen this in our slides on this topic. And we are going to use the shuffle split CV as a cross-validation strategy. Here we have initialized this cross shuffle split CV with 10 different folds, so we'll get 10 different scores, one for each fold. For every fold, there are some examples that are set aside as test, and we calculate this cross-validation score on that test set. Since there are 10 different test sets, we get 10 different scores through this particular method. And these are 10 different scores that you can see here. And now since we have 10 different scores, we report the mean and the standard deviation in these particular scores. So we see that the negative mean squared error is, the mean of that is minus 0.52, and the standard deviation is 0.022. So you can see that most of the scores are more or less comparable, and that is also that we can also verify through the standard deviation value, which is fairly low. So since we were calculating the score, which is negative of the mean squared error, we got this particular number. Now we want to convert, let's say, this score to the error. We can convert it as follows. So we can take this particular score multiplied by -1, and we get the mean squared error. Now we can see that the mean squared error is 0.52, and The standard deviation is 0.02. Here we use negative mean squared error as a scoring parameter. There are some more choices that are available as scoring parameter, which is like explained variance, max error, negative mean absolute error, negative root mean squared error, negative mean squared log error, negative mean absolute error, negative mean absolute percentage error, and R2. We have seen these choices in a bit more detail in the presentation on this topic. So the cross-val score just gave us score based on cross-validation. If we want to, let's say, access the models trained in each fold along with some other statistics like train error, we can use cross-validation API. And cross-validation API has pretty much the same parameters like cross-val score. It takes the estimator, then the training feature matrix, training labels, the cross-validation strategy, which is shuffle split CV, the scoring metric, which is negative mean square error, and we also set these two parameters to true, which is return train score and return estimator. So return estimator, when we set to true, we also get the estimators that were trained on different fold. And when we set this particular parameter, we also get the score on the training folds. And remember that these two by default are false, hence we need to explicitly set them to true. So as a result, we get a dictionary object that has got trained estimator, time taken for fitting and scoring the models in cross-validation. We also have training score and a test score. Let us print the content of the dictionary for us to examine. So you can see that there is a key and a value. So there is this estimator which has got 10 different estimators that were trained on 10 different folds. We have fit times, which is again a list of 10 numbers. This is the time that was taken to fit model in each fold. Then the score time, in the same manner, the time it took to calculate the score in each fold. Then we also get 10 different numbers here, which are test scores as well as the train scores over here. And remember, these are the scores, and higher the scores, the better the performance. So you can see that our performance in general is better on the training set than the test set, which is what we normally get. Now we'll compare the training and test error to assess the generalization performance of our model. However, we have training and test scores in CV results dictionary. We multiply these scores by -1 and convert them to errors. So we multiply train score and test score by -1, and that way we have now the errors. So the mean squared error for the training set is 0.51, and for the test set it is 0.52. So in training set there is a smaller standard deviation than the test error. So training has got a better error or the lower error, hence training performs better than the test. And these scores are comparable, but they are still high, and that actually points us to possibly the problem of underfitting. We'll confirm that by plotting the learning curves. The learning curves has got slightly different meaning in the context of Sklearn. In machine learning techniques course, we talked about learning curves as the iteration on the x-axis and the loss on the y-axis. So here this is a slightly different kind of learning curve where we have the training set size on x-axis and we have the error on y-axis. So what has really changed is the x-axis. Here instead of iteration we have training set size as the x-axis. So for this we'll be using learning curve API that calculates cross-validation scores for different number of samples as specified in the argument, which is training underscore sizes. Let's check out the learning curve API. Meanwhile, here there is a code snippet for plotting the learning curve, and we are hiding it because this has got code for plotting the learning curves. So let's see how to call the learning curve API. So learning curve has got the estimator, training and test feature matrix and labels, the cross-validation strategy, the scoring metric, and its number of jobs, which specifies whether we should be using parallelism and how much parallelism we should be using in this particular API. And we set return times to true, and we specify training sizes. So all these arguments up to this point are exactly same as cross-val score or cross-validate. So we now have return times and training sizes, and training sizes is the most important argument because here we specify what is the range of values that we should be using in training. So we use values between 0.2 and 1, and there are 10 such kind of values that will be used. We get some such kind of a plot after plotting the training examples versus mean squared error. We have training examples on x-axis and mean squared error on y-axis. So you can see that there are 10 different points with varying number of training examples, and for each of these points there are corresponding mean squared error that we are plotting on the y-axis. So we can see that both curves have reached a plateau and they are close and fairly high. So few instances in the training means that model can fit those examples perfectly. And we can see that when the model is trained on a few instances, the error on the test set is quite high. And as we add more training examples, the test error gradually comes down. So this learning curve is a typical of an underfitting model. We also study how the model training scales as a function of number of examples. So we have fit times, and we plot the training examples versus fit times. And you can see that as the number of training example grows, the time that it takes to fit the model also increases. Let's examine the weights and the variability in the weight vector across different folds in cross-validation. So here we have a box plot for linear regression coefficients that we obtain in different folds. So you can see that this is a box plot for the weights that are assigned to longitude across different folds, and the variability is quite small because box plot is quite compact here. Whereas in average bedroom, average rooms, and population, there seems to be some outlier weights. In most of the other cases, the box plot is quite compact. That means there is a lesser variability in the weights that we obtain across different folds. And we can check that by also calling the describe on the weights data frame. And you can see that the standard deviation in most of the cases is fairly small, except for these two cases it is higher than the other cases. And you can also see the presence of outliers in case of, let's say, population where the 75th percentile and the max has some difference, right? So we have actually obtained multiple models in cross validation, and we need to select one model which gives us the best performance on the validation set. So we can find out the best model by calculating the one that results in the least error. We can found that by calculating the np.argmin on the test error. We get the index of the best model, and we can access the best model from the from the from the dictionary that was obtained in cross validate. We can examine the model coefficient of the selected model in the same way as we examined the coefficients earlier in the collab. Finally, we also want to find out the how the predictions on the test points look like compared to their actual values. So we use cross-val predict API in order to get the prediction on the test points. This particular API gives us the score for points when they were part of the test set in cross-validation. We calculate the mean squared error based on the, the actual training labels and the labels that were obtained in cross-validation. And we simply plot the graph of the actual label and the predicted label. Ideally, if we have perfect classification, all the labels should be along this 45-degree line. But we can see that most of the points are scattered around this particular line. And that shows the amount of error that we have in prediction. So if we carefully examine this graph, you will find that the model seems to be all over the place for this particular value, which is label 5. For this value 5, we are predicting all possible values. And there are some negative values which do not make much sense because house price cannot be negative. We can fix this by adding a constraint on the weights to be positive. So at this stage, normally in the data in your machine learning project, we perform error analysis and check where the predictions are going wrong. Then we can revisit the model construction through feature by obtaining additional features, applying different preprocessing to the features, or changing the model. So in that way, we make necessary course correction to get better performance in the next run. So that's where the iterative process of model building comes in. And once you finally build a model, we obtain the predictions on the test set. And remember, this test set was set aside. We did not use it throughout the training process. And now we are using the test process. Now we are using the test set now that the training is over in order to estimate how the model will perform on the future examples. So we call the predict function on the selected model. By supplying the test feature matrix to it, we get the test predictions. If the test labels are available to you, you can also we can also plot such a plot. Normally in real life, the test labels may not be available when you are using the model in production. Hence, we have not added it over here. Finally, we report the model performance on the test set. And for that, we use the scoring method. We can also use any other metric of our interest like mean squared error or mean absolute error. And all the scoring metrics take the actual labels and predicted labels and provide us the metric. Now here we obtain two metric, one with CV and another one without CV. You can observe that The cross-validation based model has slightly lower mean squared error than the model without cross-validation. And hence this model performs, we can conclude that the cross-validated model performs better than the one without cross-validation. So as an exercise, I would request you to change the scoring schemes and compare the results across different metrics. Another exercise is to repeat all the modeling steps with HGD regressor API that implements that trains the linear regression model through iterative optimization. So this was the demonstration of linear regression model with normal equation. We have tried to use different modeling steps in order to give you the flavor of different Sklearn APIs that are available at our disposal. In the next video, we'll look at how to build a baseline model. Till then, namaste and goodbye.